Hello everyone, my name is Guimu Guo, and I'm a PhD student from the Computer Science Department of the University of Alabama at Birmingham. I will present the next two section, mainly on the Gsynchro system. First, let me introduce the target problem of Gsynchro. That is to find qualified subgraph instance from a big graph. One example application is to map dense subgraph structures such as cliques, pseudo-cliques, and many other dense subgraph definitions. For example, cross-cliques are a kind of pseudo-cliques that require each node to be connected to the majority of other nodes. Many of these dense subgraph structures is useful in real applications, such as finding social communities and co-expressed genes. Another example application is subgraph matching. We are given a query graph. We want to find subgraph instance that match it in a big data graph. This query is useful in searching knowledge graph and biological networks. A key feature of those problems that Gsynchro targets is that their time complexity is high, often because of the giant search space rather than the data volume itself as in conventional data-intensive application. In this slide, we show how we can explore the vertex site of the result subgraph by depth-first backtracking in a set enumeration tree of all possible vertices. This, for example, applies to our clique finding problem. During this process, we will keep a set for the vertices already in subgraph and another set for the valid candidates to add. To avoid redundancy, we only add new vertices into the site if their IDs are larger than those vertices that are already in the site. For example, to get ABD, we do not grow BD by A, but rather grow AB by D. In traditional single-thread algorithm, we usually solve these problems by divide and conquer. Let's backtrack on the nodes in our previous search tree. Let's illustrate by considering the problem of finding maximum cliques. Specifically, since each clique is a complete graph, where every pair of nodes are one hop away, we can construct one hop equal network around each vertex and find clique from those subgraphs. If a vertex, say V1, has a high degree and so the subgraph around it is still very big, we can recursively divide it into small overlapping subgraph for further learning. Now let's zoom in that subgraph and assume that V1 is already in our results clique. We can then consider two cases, those cliques containing V3 and those without V3. The pink subgraph assumes V1 and V3 are in our clique. We can continue marking cliques in this subgraph by kicking out those vertices more than one hop away from V3. For those without V3, we can further divide them into those with V4 and those without. The pink subgraph assumes V1 and V4 are in our clique, and we kick out those vertices more than one hop away from V4 from the subgraph, and then continue the learning. We can then continue on the remaining subgraph and divide it if necessary. In fact, the mining itself follows this recursive procedure and explores our set enumeration tree in depth-first order. We next review the related works that tackle the dense subgraph mining problems. Earlier works use MapReduce, but it is found that the IO-bound MapReduce framework is not suitable even for triangle counting, as the performance is 10 times slower than the single-thread program. Due to the popularity of think-like vertex programming models, there are some works solving dense subgraph mining using vertex-centric programs. However, in vertex-centric paradigm, vertices notify other vertices about their value updates by sending messages along edges, makes the execution network IO bound. Also, the programming is not intuitive for subgraph mining, since the vertex-centric programs operate in the unit of vertex and are usually for computing values for vertices, not for finding subgraphs. Recently, a number of systems were proposed for graph mining based on the idea of subgraph-centric programming, which is more intuitive to program dense subgraph mining algorithm. However, they only address the programming friendliness issue, but not the low efficiency issue, as their execution agents are still I/O-bound. Gsynchro is the first work in this direction, which constructs candidate subgraphs to mine upon around each vertex using k iterations of breadth-first search. However, this is conducted by k MapReduce jobs, which makes the precise network I/O-bound. Each MapReduce job also needs to load and dump a huge amount of intermediate subgraphs via Hadoop distributed file system. The subgraphs are then finally distributed for concurrent mining with other MapReduce job, which serves from the curse of the last reducer. Arabisk proposed a user-friendly programming interface for graph mining called embedding-centric programming. Here, an embedding is a materialized subgraph, and these subgraphs are growing in an increasing size for tracking. Arabisk is a distributed system where every machine needs to keep an entire data graph in memory, and subgraph materialization is the dominant cost. In contrast, our Gsynchro uses node backtracking in serial mining algorithms as much as possible to avoid the cost of materializing subgraphs. Arabisk's API also covers the problem of frequent subgraph patterning, which requires Arabisk to conduct subgraph isomorphism check on each newly materialized subgraph. But such check is not needed in other subgraph mining problems that we consider. Recall that our set-enumeration tree perfectly divides the search space and avoids redundancy by comparing vertex IDs. In summary, Arabisk's API is simple, but not amenable for efficient execution. Check out our prefix FPM system presented earlier by Dr. Yin for more efficient solution for frequent patterning. In fact, removing the slow network communication can speed up the computation, as is realized by the upstream system. But as a single machine system that runs in the out-of-core mode, upstream is still disk I/O bound. Another system, Nuri, proposed to find top k result subgraphs rather than all of them. But Nuri is a single-threaded Java program. All the systems we reviewed so far do not scale their performance with the number of CPU cores they use. For example, on a datasite called YouTube, Nuri takes over 1,000 seconds to find the click. If you use our Gsynchro system on the same graph with 1 million vertices, it takes only 9.4 seconds on one multi-core machine. You are welcome to check out our demo on the Gsynchro website. As a side note, Frank McSherry has criticized the I/O-bound performance bottleneck of existing big data systems, whose performance is often only comparable to a single CPU core's throughput. Our research group has proposed and been working on a new programming paradigm called T-Thinker, or think like a task, which targets high complexity divide and conquer algorithms over big data. The idea is that if your computing cost is superlinear to the data size, then the cost of computing a task on a subset of your data is expensive enough to justify the linear I/O cost of collecting the data set, as long as the computation and the communication is well overlapped. Of course, we should still keep the programming model more general and friendly than using the conventional HPC library. there are actually a lot of problems that are amenable to divide and conquer. For example, the algorithms of marrying cross-clicks and key places are both amenable to divide and conquer, and they can be straightforwardly implemented on our Gsynchro platform. We have already implemented cross-click marrying on Gsynchro, and the program got a speed up of over 200 times in our small 16-node cluster. Here is a brief history of our Gsynchro system. Gsynchro was originally a prototype where .env proposed a Vertex polling-based subgraph API. But as a prototype, the execution engine is just to make things work, and it does not even have a multi-threading support. It also has float descents. For example, tasks access vertices in a bulk synchronous parallel manner. And to reduce memory overheads, subgraphs are saved to disks, but a bad task scheduling strategy leaves many subgraphs on the disks, leading to an expensive I/O cost. Since a full-fledged Gsynchro system will take time to develop, the student who helped implement the old Gsynchro prototype simply added multi-threading support and termed the result system Gminer. But it inherits all the flow descents and leads to a poor performance when an input graph gets big. Gminer follows the same API as Gsynchro, as the Gminer paper clearly indicated. Please check out our new Gsynchro website where you can get great documentation. Our research group will provide full technical support. Here is an overview of Gsynchro in a cluster of 3 machines. Gsynchro loads the input graph from each DFS, where each machine loads a fraction of vertices along with their adjacency lists into the local table. Tasks are initialized from each vertices in the local table. A task can grow its subgraph by requiring neighboring vertices or actually their adjacency lists. To allow multiple tasks in a machine to share remote vertices, a remote vertex cache is maintained, but it has a capacity limit to keep memory bounded. Each computing thread maintains a local task queue to keep it busy. This is the key to our scalability to CPU queues. When a task queue is about to be empty, new tasks will be refilled to this task. Where if more tasks need to be added to a full task queue, the last batch of tasks in this queue will be spilled to disk and to be refilled by other computing threads later. This allows memory consumed by tasks to be bounded. Here is an illustration of how vertices are partitioned by the local vertex tables of all machines, which form the distributed key-value store where a task can pull the adjacency list of a vertex using its ID. Here is an illustration of the remote vertex cache. For example, where vertex 8 is not in the machine M0. If a task on M0 requires the vertex 8, it will be pulled to the cache. Note that if other vertex on M0 also needs 8, it can then directly access it in the cache without sending a duplicate request. Here's the task-centric programming model of Gsynchro. The first user-defined function specified how a task is spawned from an individual vertex. The second user-defined function specified how a task grows its subgraph from the surrounding vertices adjacency lists, which are pulled into the frontier array the last time the compute function is called. A task calls compute in iterations to expand its subgraph until all needed data are ready, after which the task then mans the constructed subgraph. When vertices are being pulled, the task is suspended so that the CPU cores can be released to process other tasks. A task can pull a vertex that is on its subgraph boundary. It can also split the subgraph into multiple new tasks for concurrent processing if the subgraph is big. The new tasks can be added to Gsynchro by calling the addTask function. The next question is how to design a remote vertex cache so that tasks can access vertices concurrently, where the requested vertices can be continuously added when received from remote machines, and the vertex no longer needed by the tasks can be evicted to make room for new requests. One solution is to hash vertices into different buckets using their IDs, so that if two vertices are in different buckets, their processing can happen together. In this slide, we assume vertices are hashed to 10 buckets by hashing their ID module 10. Each bucket is protected by a lock, so that only one operation can be carried out each time. A bucket has 3 containers. Gamma table keeps the adjacency lists. It also keeps the counter to track how many tasks lock a vertex. Z table or zero table tracks which vertices are no longer needed by tasks. With Z table, we do not need to scan the entire gamma table when evicting vertices. R table or request table keeps those vertices that are requested by tasks but whose adjacency lists are still being transmitted and not yet received. It also has a counter to track how many tasks request each vertex, which avoids sending the same vertex request many times. We next illustrate how these containers are used. For example, if some tasks request removed vertices 10 and 11, and their adjacency lists happen to be in gamma tables, then we simply add their counters by 1 to indicate that one more task is holding them. Here, vertex 10 is also removed from Z table, as its counter is no longer 0, and it cannot be evicted anymore. Next, assume a task finishes a round of compute function call and releases its hold of the requested vertices such as 12 and 13 here. Then we need to decrement their counters in gamma table, and since vertex 12's counter becomes 0, it is added to Z table to allow eviction. Now assume a task requests the vertices 20 and 21 from our cache, and their adjacent lists are not already in gamma tables. Then we need to add them to R tables. Here, 20 is already in R table, so we simply increment its counter to avoid sending another redundant request, where 21 is newcomer and thus the request is added to the sending queue. This is how R table avoids sending redundant vertex requests. Now assume that vertex 22's adjacency list has arrived, and in R table, 22 already has 3 task requests. We then move the entry along with its counter 3 to gamma table, indicating that 3 tasks has holding vertex 22. We also have a garbage collector that periodically scans Z table to evict vertices. That's why we need a small size Z tables. If we let GC scan the large gamma tables, it will take a longer time to lock and check each bucket, and hence reducing concurrency. An evicted vertex is removed from both Z table and gamma table. Next, we look at Gsynchro's task management. In this slide, the components in the red box are shared by all computing threads in a machine, including the local vertex table and a list of task files spilled from the task queues of computing threads, both of which are source of tasks to be refilled into the task queues. The black box on the right shows the components for each computing thread, while the third task source is a set of tasks that are waiting for the requested data to arrive. We will prioritize our refill by considering the task files first, as these tasks have been partially processed, and we want to finish pending tasks earlier than spawning new tasks, in order to minimize the number of disk buffered tasks. Now let's look at those components inside each computing thread. The task queue keeps a list of tasks to be computed by the current thread along with their vertices to request for. If the queue has too few tasks, we will refill tasks from one of the previous 3 task sources. If the queue is full but a new task needs to be added, we will first spill the last batch of tasks as a file to disk, and then append this new task. Each computing thread posts a task from the head of queue each time, requests the vertices, and if any of them are not in the cache, it will put the task into the task table shown here to wait for data. We also keep track of how many requested vertices are met. If a vertex response is received, we get the task list of that vertex from the R table. Earlier, for the ease of presentation, we mentioned we maintain a counter for each R-table vertex entry. But we actually maintain the list of task IDs instead to track those tasks that request that vertex. For each task in the task table, we add the mat counter, and if the counter reaches the number of all requested vertices by the task, we move the task to the task buffer here. Each computing thread keeps calling pop to take tasks for processing, and calling push to compute the ready tasks and add them to task queue if more processing is needed. Newly created tasks are also appended to the task queue, and tasks may be spilled to the disk. We remark that pop is only called if vertex cache and task containers have enough space. If vertex cache or task containers reach their capacity limit, we only repeat push function to process ready tasks, so that vertices can be released from the vertex cache to make room. And pop can then be restored to request more vertices for new tasks. For task stealing between machines, we will estimate the pending tasks in each machine from the capacity of local vertex table and the task files buffered on the disk for deciding effective task stealing plans. Tasks stolen from other machines are appended to our file list on the disk to be refilled into task queues of computing threads. As you can see here, Gsynchro is orders of magnitude faster than other systems, especially for big graphs. The only competitor is Gminer, which can scale well with the number of CPU cores used, but it does not scale well when the graph gets big, due to its bad task scheduling scheme that keeps a lot of partially computed tasks on the disks. We have recently further improved the Gsynchro system. The reason for improvement is that we found some dense subgraph learning algorithms to be much more difficult than what our Gsynchro IEEE paper already implemented, such as finding maximal clicks and triangle counting. This is especially true for learning pseudo-click structures such as post-clicks and keyplaces, where we found they generate tasks of drastically different running time. And a straightforward parallelization severely suffers from this structural problem with some bottleneck tasks will run forever, while most other CPU cores become idle. To address this problem, we redesigned Gsynchro's execution engine. Specifically, we added a global task queue to hold big tasks, that is, tasks that are very time-consuming. This global task queue is shared by all learning threads in a machine. Those big tasks in a global task queue will be fetched with priority, and task stealing is used to balance big tasks among machines. In this way, the big tasks can be moved around to idle threads in time, which will solve the structural problem. As we have described in previous slide, we maintain separate task containers for big tasks and normal ones. For normal tasks, we keep them by using the local task queues of respective learning threads. For big tasks, we maintain a global task queue to keep them. It is shared by all learning threads. The global task queue is also accompanied with other big task containers, such as a file list to buffer big tasks that are spared from the global task queue. Here we illustrate the structural problem suffered by the old Gsynchro, and how our new design addresses this problem. In this animation, big tasks are highlighted in red to differentiate them from normal tasks that are in blue. If we only let each learning thread to buffer pending tasks in its own local queue, big tasks in the queue cannot be moved around to idle threads in time. Big tasks can be stacked by other big tasks located earlier in the queue, causing the head of line blocking and the structural problem. In our new Gsynchro, we keep a global task queue for each machine, which is shared by all threads on that machine. The big tasks will be stored in the global task queue. Since the main performance bottleneck is caused by big tasks, they will be processed with priority by the local learning threads. Also, task stealing is conducted only on big tasks to balance them among machines. Next, I will introduce how to design the subgraph mining algorithms on Gsynchro. We call the programming model as think like a subgraph, since each task maintains a subgraph that the task creates and moves upon. Here are a few features of a typical subgraph mining algorithm. First, they usually follow a divide and conquer paradigm and can be divided into multiple mining tasks in Gsynchro for parallel computation. However, some tasks may be very expensive, running for a much longer period of time than an average task. In this case, we can decompose such big tasks into small tasks. There is a challenge, however, in identifying such tasks, since in dense subgraph mining, the mining time of tasks can be highly unpredictable. We will elaborate on this in a few later slides. Recall that in Gsynchro's programming model, a task is bounded from individual vertices, and iteratively calls the user-defined compute function to expand its subgraph and to mine the created subgraph. Also recall that a dense subgraph mining algorithm can check the subgraphs using a vertex set enumeration tree, where each node corresponds to a set S of vertices already included in the result subgraph, and is accompanied by a candidate vertex set extension S to expand the subgraph weights. In this example set enumeration tree, 4 tasks are initially spawned from the individual vertices A, B, C, and D by calling the spawnTask function. The set enumeration subtree under vertex A is big, and if it is totally mined by one task in serial, the cost can be much larger than other tasks, even their costs combined. Therefore, this task can become a straggler without task decomposition. In this slide, we plot how each subgraph feature impacts the task running time. The x-axis in the 5 subplots correspond to 5 subgraph features, including vertex number, edge number, maximum vertex degree, average vertex degree, and subgraph core number. These data are extracted from the Gsynchro running profile when mining a YouTube social network for cost clicks. We can see that for about the same feature values, the time can vary a lot along the vertical direction, which is a time dimension. And this happens unless the subgraph is very small. Apparently, expensive tasks cannot be predicted from these features, even though some features, such as core number and average degree, reflect the graph density. Here is another plot for the running profile when mining cost clicks on a US patent citation graph. The y-axis for task running time is in log scale. We can again see that the time can vary a lot along the vertical direction for similar feature values. The reason for such a big time variance is that this subgraph algorithm relies heavily on pruning rules to reduce search space. And the timing when a pruning rules connection is met and thus applicable depends on the vertex connection dynamics that changes as we expand the current vertex set S, and is very difficult to predict. Since the task running time is difficult to predict, we designed a timeout mechanism to avoid straggler tasks. Specifically, we define a time threshold and decompose the task if it runs for a longer time period than the threshold. Taking the task spawned from vertex A as an example. Assume that the running time exceeds the time threshold when the task is about to check A, B, D. Then the task will be decomposed into 3 tasks by backtracking. For example, at the second level, node AC also times out, and its subtree becomes a new task. Based on whether a task has a big workload or not, which can be judged by the size of vertex candidate set, each decomposed task will be added either to the global task queue or the local task queue of the current mining thread. The decomposed tasks may time out again for further decomposition in their future computation. The straggler tasks will not be the bottleneck by using this timeout mechanism. Next, we illustrate some pruning rules that can be applied in Gsynchro. Firstly, in the set enumeration tree, each node S only expands with vertices whose ID are larger than those in S. So a task never pulls vertices whose IDs are smaller than the vertex that spawns the current task. For different graph mining algorithms, we also have specific pruning rules for them. Taking maximal cross-click mining as an example, where a cross-click is defined as shown here. Given a minimum degree threshold gamma, a gamma cross-click is a subgraph where each vertex connects to at least the gamma fraction of the other vertices in the subgraph. There is a pruning rule saying that given a gamma no less than 0.5, the diameter of a gamma cross-click is at most 2. This can be easily proved as follows. For any two vertices U and V in a gamma cross-click, based on the definition, they should both connect to at least 50% of the other vertices. If we assume the neighbors of U and V do not overlap, then the total vertex count of U, V, and their neighbors will become one larger than the cross-click size, which leads to a contradiction. As a result, U and V must share a neighbor if they are not directly adjacent to each other. Since U and V can be any pair of vertices in the gamma cross-click, the diameter of the cross-click is at most 2. We can prune candidate vertices using this property. Specifically, when extending S, we can prune extension S not to include those vertices which are not within 2 halves from any vertex in S. A similar pruning rule applies to click mining, where only direct neighbors of the vertices in S need to be extended. When mining maximal clicks, we also have another pruning rule called cover vertex-based pruning, which we will illustrate here. Let's assume that vertex A has the highest vertex degree, and we move all its neighbors W, X, Y, Z to the end of the candidate list. Then we can prove that when expanding S with one more vertex, we do not need to explore those neighbors. This is because any gamma cross-click formed only by these neighbors cannot be maximal, as adding A to the click gives a larger gamma cross-click. Note that A is connected to all vertices in such a gamma cross-click, so gamma will not decrease. We see that A covers W, X, Y, Z in this case. This is actually a simple special case of cover vertex-based pruning, and our cross-click mining program uses many more sophisticated pruning rules. Please refer to our VLDB paper for more details. In Gsynchro, we also support an aggregator, which allows users to aggregate results computed by tasks. Aggregator values are locally aggregated and periodically synchronized to get globally aggregated values. Aggregator is useful for searching space pruning and subgraph counting. For example, to find maximum clicks, we can use aggregator to track the maximum click currently found. A task will be pruned by terminating itself when it cannot generate a larger click than what is reported by the aggregator, even if all candidate vertices in extension S are included. In conclusion, our think-like task programming models are very efficient and user-friendly, and a perfect match for divide and conquer algorithms. As a representative system, Gsynchro is very promising direction, and there are still a bunch of algorithms waiting to be parallelized with Gsynchro. Our group is currently working on multiple graph mining algorithms that require non-trivial parallel adaptations with Gsynchro. And a series of research papers are to be expected in the next couple of years. You are very welcome to follow our work and try out Gsynchro. Please also consider to follow our work. This direction is very promising with low competition, like Prego research 10 years ago, and were definitely worth your research investment. Thanks for your attention, and please feel free to ask questions. We will answer your questions from now on. Dr. Yan is also finding outstanding students to join our research group for this line of research. Please feel free to send him an email if you think you are a good candidate.